Now we want to look at two final tests for absolute convergence of a series, and they kind of go together just like the direct comparison and the limit comparison test went together. The first is called the ratio test, and so what we're going to do is we're going to look at some series. It'd be the sum of the terms a sub n. They're all going to be here. We should really let this be positive. We could say eventually all positive. And we're going to look at the limit of the ratio of successive terms, okay? And the theorem says that if that ratio converges to some number row that's less than 1, then the series converges. But if the limit converges to a number greater than 1, the series diverges. And if it's equal to 1, the test is inconclusive, okay? So let's look at some examples. This theory is, and the reason why this is true, by the way, I don't want to go into a long drawn out discussion, but basically what happens is, if you think about it, if an plus 1 is less than row an, eventually, or this row is less than 1, the behavior is like a geometric series. Behaves like a geometric series. Okay, and that's why this rule works. You have to go through a little more math to prove it carefully, but that's kind of the basic idea. Now, this is particularly useful when we have factorials, and let me show you two examples that can occur pretty commonly. The first we're going to see when we're looking at Taylor series. So let's just let x be any real number, positive real, and let's look at the following series. And we're going to see that this is a series for e to the x. Okay? And we want to ask the question, does this converge? And let's use the ratio test. Notice all the terms are positive, okay? So if we look at this limit as n goes to infinity of an plus 1 over an, this is going to be equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial over n factorial times x to the n, which is going to be the limit as n goes to infinity of x over n plus 1, which converges to 0, which is equal to rho. It's less than 1. Therefore, by the ratio convergence, by the ratio test, this converges. The series will converge. Okay. Now here's another series that we really couldn't do any other way. So let's look at the following series. Put a little space here. So now let's consider an example where we have the following series. And I'm going to be careful and write it like this. And it's really not obvious what this series should converge to when we first look at it. Okay, it's a kind of strange looking series. But let's go ahead and try the ratio test. So if we look at the limit as n goes to infinity of the successive terms, and we're careful about these factorials, it's going to look like this. And then this will be n factorial times n factorial over the quantity 2n factorial. And when we get down and we evaluate this, what we're going to find is that after we do a little bit of cancellation here, this will become 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. And so this limit will converge to 4. That's our row, which is greater than 1. Therefore, this is going to diverge. Therefore, by the ratio test, the series diverges. Now, next we're going to look at the root test. And the root test is going to be somewhat similar to the ratio test, except now we're going to look at the nth root of the nth term and take its limit. And again, we're going to let that limit be equal to rho. If rho is less than 1, the series converges. If it's greater than 1, it's going to diverge. And again, if it's equal to 1, it ends up being inconclusive. We cannot tell. Okay? So let's go ahead and try this. Let's try the following example. Let me pull out an example here that I have. Okay. So let's look at this series right here. Sorry, that's n cubed, sorry. Okay, and notice this is a little hard to judge initially because the e to the minus n terms are decreasing, but the n cubed terms are increasing, okay? So let's go ahead and try the root test. So we're going to take the limit as n goes to infinity of the nth root of the nth term. And when we do that, I'm going to split this up like this. This first term becomes e to the minus 1. And the next term becomes the nth root of n raised to the third power. Okay? And we know that and now we can go ahead, we can factor the e to the minus 1 out, and there's nothing there. And if we wanted to do this carefully, okay, we can go back and we can use the fact that if we have a continuous function like x cubed, we can use our limit theorems for continuous functions. Remember we said that if we had an equal to f of n, and an converged to gamma, and f was continuous at gamma, then the limit as n goes to infinity will be f of, f of an, If we have some function f of an, and an goes to gamma, and f is continuous at gamma, then the limit of f of an goes to f of gamma. Okay, so this is like our f of an. So this goes to 1, and x cubed is continuous at 1, so this goes to 1 over e, which is less than 1, and therefore this thing converges. Okay. Let's maybe do one more. Okay. This is a kind of hard-looking one. Suppose, for example, we wanted to look at this series. Again, the fact that we see a power suggests we should use the root test. So if we try the root test, okay, it's going to be the nth root of n. And we take the nth root down here, this will just be the square root of ln of n. Okay. We know that the top converges to 1, and we know that the bottom converges to infinity. So this goes to 0. which is less than 1, which implies that this series converges. Okay, that's all the theorems we have for series convergence.